I have to start this over again, reset and start. So possibly the little camera is going to be missing a little bit of this, but I was just saying that the green edges are the stuff we've taken, the black edges are the edges that S, the other edges that S contains, and the red edge is this thing, is this edge we've just taken, which is incompatible with S. It creates a cycle. Okay, so when you go around these black edges, well, actually all of the black edges, what can we say about their cost compared to the red edge? Watching the chat. So remember, we're processing the edges in non-decreasing order by weight. We have processed this green edge. So this green edge is, the green edge is cheaper than the red edge, or at most as expensive. But these black edges, they cannot be cheaper than the red edge. Otherwise, we would have processed them first. So they're equal, their cost is equal or larger. Okay, in which case, we can take any of these black edges, maybe this one, and we can erase it. Okay, so I'm gonna actually, it's dashed. Okay, we can just erase it. And now we get a tree, because if you take a tree and you add an edge and create a cycle, and you take another edge out of that cycle and delete it, then you've got a tree, a different tree, but still a tree. Because if you have n vertices and it's connected, well, you haven't disconnected anything because you've just broken a cycle. And you have n minus 1 edges, it's a tree. Okay, so now we have this other tree, and the cost has not gone up because we've added the red edge, and we've deleted an edge which was not cheaper than the red edge, so the cost didn't go up. So we have another solution which extends all of the stuff that we already took, the green edges, and it contains the red edge, and then it contains more stuff, and it's not more expensive than S, so it's an optimal solution as well. So we're going to call this S prime. Okay, so now I need the space. No, I'm just going to say it. Okay, so if we take the edge, if S also takes the edge, fine, S extends our subsolution. If S doesn't take the edge, we can take S and do an exchange. This is called an exchange argument, and get a solution which is not more expensive than S, the solution S prime, so it's also optimal, and it extends our subsolution after I plus 1 steps. This is just ugly. I'm going to erase that and write this. Okay. So, good. So this works whether or not we take the edge. So by induction, Kruskal's algorithm produces an optimal solution. Because if you haven't messed up before you've taken any steps, and then if you haven't messed up by the ith step for I greater than or equal to 0, then you don't mess up on the I plus first step, then you don't mess up. By induction, you don't mess up, so you end up with an optimal solution. You actually have to show that you terminate as well. There are not an infinite number of edges, so yes, the algorithm terminates. That's not an issue on this problem, but yeah, for stuff like network flows, you actually have to, it's sometimes not obvious how you prove termination. So, Kruskal's out. Now, I want to emphasize that this part, sort of this template, doesn't change for greedy algorithms very much, right? I want you to learn this. before we take any steps, or after we've taken 0 steps, our empty subsolution can be extended to an optimal solution. Assume that after I steps, our subsolution can be extended to an optimal solution S. Then this is the tricky part. You have to show this after I plus 1 steps, our subsolution can be extended to an optimal solution S prime. It's not enough to just say that. You actually have to show that, because greedy algorithms do not solve all problems. So some people just say this, but you have to argue, for example, doing this exchange argument on the tree, why can I add this edge, then I can delete this other edge, because we're processing this order, blah, blah, blah. Okay, now we're going to do Prim's algorithm, which is similar, but this argument is a little bit trickier. So the argument for this step is sort of where you have to actually pay attention to what you're doing, the actual problem you're working on. And then by induction, if you can prove this, then you get an optimal solution. I taught this a few years ago, and every time I teach this, like, before we take any steps, blah, 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 and I hammer it in. And then on the exam, nobody wrote this. Nobody talked about before we take any steps, our empty subsolution can be. Nobody said anything about that. Why? Why do you think I went over this so many times? So yeah, I'm gonna ask, so you're gonna have to write something like this on the midterm, on the exam, whatever. I don't just love saying this. Okay, so let's do prims. So prims, and why am I showing you all these different algorithms for the same problem? Because they have different features, okay? I could almost leave this on, but just to sort of drive the message home, I'll probably write it out again. So prims, once again, we have the same graph. Which goes like this. And these two are not connected, and then it goes like this. A, B, C, D, E, F, G, H. I is connected to G. I, and this is 8, 4. 8, 4, 11, 7, 2, 6, 1, 2, 4, 8, 7, 9, 14, 10. Okay. So, why would we do another algorithm? So does the red edge have a greater cost, or the black edges have a greater cost? The black edges, because of the order we process these, not these black edges, but in the tree that was down here, the black edges, we can say they do not have a smaller cost. They might have an equal cost, but they do not have a smaller cost, because if they did, we would have processed them first. Now, that argument is not quite going to work when we do the proof of correctness for prims. Okay, the circumstances are a little bit harder. Not much. Okay, so Prim's algorithm. Why would we want another algorithm? Well, suppose that you're doing this road paving thing, but your road paving equipment is kind of fragile, and it can't go over dirt roads. Okay, it can pave a dirt road, but it can't drive along a dirt road and then pave something else. It can drive along a dirt road only if it's paving it as it's going, right? Because you have like some paving thing stuck out the front, and then your delicate actual paving vehicle goes on behind it on the paved surface. I don't know if this is realistic. I'm a theorist. I have never been in charge of paving anything, not even a driveway. Okay, but let's suppose that you have road paving equipment and it can't drive over dirt roads. So you can't do Kruskal's algorithm or like, oh, add this edge, now add this edge over here, because you can't get from there to here along paved roads yet. Just like imagine some situation where you don't want a forest, you actually want a tree. Okay. Where do people want their road paving equipment to be situated at the beginning? I'm just going to check that this is recording. Yes, it is. So pick a town from A to I. A. Okay, good choice. Okay, so in the beginning, the road paving equipment is at A. So Prim's algorithm says you have a tree. Okay, so at the beginning your tree is just one vertex. It's not a forest, it's always going to be a tree. Now, you look around and of all the edges incident to your tree, you choose the lightest one. Okay? And then if it doesn't create a cycle, which means if it doesn't go between two vertices that are already in your tree, you add the edge. So what's the cheapest edge that's incident to this tree? Looking at the chat. There are two edges. One has, okay, AB, yes. Does it create a cycle? Does it connect is it between two vertices on my tree? No. So I'm going to add AB. Now I have two more edges, right? So it's so my tree, I'm just going to draw it down here. So I have A and B, and before I just had AH and AB incident to my tree at A, but now I also have BC, BH, and AH. So I actually have a tie. I have two edges which are incident to my tree, which don't go between vertices of my tree. Actually, which one would we like to process first? BC. Okay, so BC spoke first. So BC. So it doesn't create a cycle. C is not in my tree yet. So I'm going to add BC. Okay, and that adds, that means now I'm also incident to CI, CF, and CD. Which edge is lightest? Now remember, we're still comparing with this edge, okay, well, just this edge and this edge are incident to A and B. Okay. CI, yes, 2. Does it connect something to something already in my tree? No. So I take it. So now I get IH, IG. What is the cheapest edge incident to my tree? For C, do we compare it when summing the edge weights from A? No, this is, you're only adding things and you're just comparing edge weights by themselves. You have to like keep sums later in the course when we're doing Dijkstra's algorithm, but not now. CF is a 4, it's bigger than this and this and this, so yes. Does it connect two things that are already in my tree? Nope. So I add CF, which is going to be down here somewhere. Now, this connects to FG and FE and FD. What's now the cheapest thing I can add? FG. Does it connect to? Is G in my tree already? No, it's not. So I add this. Now, and then, now what? FG. So now what's my cheapest edge incident to my tree? Notice this is always a tree. Okay. HG, yes. Is H in my tree? Not yet. I add this. And then, okay, what's next? GH is some, okay. Next edge, this incident to the tree. Almost. But this one. What about this one? When it creates a cycle, so we're going to process IG next because I think it's next in order, and we're not going to take it because I is already in my tree and G is already in my tree, so we can't take it. It would create a cycle. Right. So now we consider CD. Well, actually, we could consider IH. Doesn't matter. I mean, they're tied. Okay, we consider CD. D is not in the tree, so we add it. CD. And now we consider IH. IH is in the tree. I is in the tree. It would create a cycle. We don't take IH. And now we consider AH. A is in the tree, H is in the tree. You can't take it because it would create a cycle. CD is not a cycle yet. I don't think I have any cycles yet. Okay, so we can't take AH. Next thing is DE. D is in the tree, E is not in the tree, so yes, we can take this. And then actually, you could notice that we've actually connected everything, but we're just going to run the algorithms to completion. FE, F is in the tree, E is also in the tree, we can't take it, it would create a cycle. No. And then the only other thing, we consider DF. D is in the tree, F is in the tree, we can't take it. And we end up with a tree. Okay? So, this is not the same tree that we had before, right? Because before we had this edge and not this edge. So the solution is not necessarily unique, and it depends on how you break ties. So this is prims. So actually, if we'd broken ties, we could have got the same tree because of this example. So, do people understand the algorithm? Sort of. I mean, it's nice because you always have a tree, so your road building machinery doesn't have to drive. If it starts at A, then it goes to B, and then later, so it goes to C, and then if it turns out you did CI and later you want to add CD, it just has to go back to C and add. So it just has to drive around a lot. The way you stated it made it sound like you couldn't go back. Sorry, no, you can go back. because once you've paved this road, your road building vehicle can cross it. Okay. Yes, you can definitely go back, otherwise this wouldn't work. Oh, you can't go back in the sense that if you take an edge, then it's in your solution. If you throw the edge away, it's not in your solution. You can't change that decision. But if you take an edge, then you can later, just because I add CI doesn't mean I can no longer add anything incident to C. Okay. So, just checking to see how much time we've got. 4 minutes. So, ooh, this is going to get a bit tight. So what's nice about prims? You always have a tree. Okay. What's not so nice about prims? Well, with Kruskal's, you just sorted the edges, and then you just process them in sorted order. In prims, you have these, and then you're adding the edges, so you're keeping a priority queue. First I just have a priority queue with AB and AH, with AB with priority 4 and AH with priority 8. And then when I connect B, I have to add BH with priority 11 and BC with priority 8. So I'm using a priority queue instead of just sorting. Right? So it sounds like there's more of a headache with prims. Okay, so you can't just do a sort. You have to use this priority queue element, priority queue data structure. Now, so there are pluses and minuses. Later on, we're going to see that Kruskal's is actually not as easy to implement as we think. Okay, but first, let's do the proof of correctness for prims. Everybody, along with me. Before we take any steps, or you can write this when we have taken 0 steps, which is the same thing, our empty subsolution can be extended to an optimal solution. Suppose that after I steps, our subsolution, same stuff as before, can be extended to an optimal solution S. Why did I erase this? So as I said, I don't know why people didn't write this those few years ago, because there's this rule that like if the professor says it once, like listen. If he says it twice, write it down. If he says it 3 times, it's going to be on the exam. If he writes it on the whiteboard multiple times, then it's probably going to be on the exam. Okay, so this is the problem. We show, this is not quite the same wording, that after I plus 1 steps, so I'm just writing it, we show to emphasize our subsolution can be extended to an optimal solution S prime. Now, we're going to sort of do the same thing. We have now the green edges have to form a tree, right? Because after I steps are... Okay.